shake your body, baby, do that conga, no.
The electric vehicle team designs and builds electric motorcycles and needs a reliable way to test and tune their powertrains. That's where a dynamometer comes in. It measures motor power produced for a known load. This project combines electrical and mechanical hardware with a custom MATLAB software interface. Up next, we'll demonstrate the system's electrical hardware and software, which control the motor that loads the bike's drivetrain. Alright, so from the custom MATLAB software, we are going to command a torque, at which point we should start hearing the motor make some noise. Then we will choose a RPM limit for the motor. We'll set it to 200 RPM, and then we'll hit enable, and the motor begins to spin. In real time, we can adjust the torque and maximum motor speed commands. We can have them increase to make it spin faster, all the way up to 500 RPM, or we can switch the sign on the torque command to make the motor switch directions.
The mechanical system can be simplified into 4 interdependent subsystems. First, we have the base plate, which is a 1/2-inch thick steel plate designed to withstand the extreme loads of operating the dyno. This plate allows for the mechanical hardware to be bolted directly to the plate for easy installation. The steel plate is supported by a 1/4-inch thick steel square tube to prevent bending of the plate and allow for transport with a pallet jack. Next, we have the powertrain, which allows for power transmission throughout the entire system. The powertrain utilizes a chain and sprocket system with universal sprocket sizes to maintain a constant gear ratio throughout the system and mimic the true drivetrains on EVT's vehicles. Both motors sit on an adjustable rail mount system that allows for motor placement adjustment and chain tensioning in the event the customer wants to use a different motor under test. Shafts coupled to the torque transducer are supported by 2 bearings on each side to protect the torque transducer from radial and axial loading. Since the dyno has an extremely high operating RPM, we also need to protect the user, which leads us to our 3rd subsystem, which is the enclosure. The enclosure is a 1-inch steel square tube frame with polycarbonate paneling to protect the user from any ballistic projectiles that may break free from the system, while also being able to keep an eye on the drivetrain during operation. This brings us to our final subsystem, which is cooling. While the motors come with their own cooling systems, we need to provide extra cooling within the closed space of the enclosure. To do this, we placed strategically located vents coupled with a fan on the enclosure to draw hot air out of the closed space and keep our system cool.